Leon. I'm a data scientist working at Toronto. I'm working at a company called Manulife, and our team kind of like do more work in the NLP field. So yeah, if you have any questions during the presentation, feel free to let me know, let the whole team know. I'll try to present my screen. I'll just do a quick intro of what we'll be covering today. And then I'll hand it over first to Weiwei to talk about some of the concepts that are gonna help us understanding the XGBoost. And then I'll hand it over to Zoe, and she will be talking about the regression tree in XGBoost. The laptop kind of like freezes. Everyone can see my screen?
Yeah, we can see.
Okay, thanks. And then the third part is the core learning algorithm of XGBoost, which is gradient boosting. There is some math details that we want to talk about today. We'll talk about why we want to learn those, cover slightly about that as well. The last part is just like some other miscellaneous stuff, including like say why it's called XGBoost, or some of the resources that I found particularly useful, like when I need to apply XGBoost, some like parameter tuning strategies, and how to basically like apply the like theories into a real world problem. Yeah, without further ado, I will pass it over to Weiwei, and let's get this started.
Can you see my screen now?
Yeah, I can see it.
Oh, great. My name is Weiwei Zhang, a master student graduate from McMaster University last year. Today, I will give you a brief review of some key concepts which is very helpful for learning the XGBoostings. So first of concept is the decision tree we learned last week. It basically is a tree structure layout of all the features and attributes for helping you predict the output with the components in it, such as the roots, nodes, and ifs. For example, we want to determine whether we lend a loan to some person. There are many attributes like the age, his earnings, his education, and his income. So as we record this diagram from last lectures, we construct a decision tree to help us determine whether we learn the loan or not. In the diagram, the yes or no or other these kind of lines are what we call the direct edges, and besides the end of and the top and the bottom, the internal the decision points we made or to split the tree is called internal nodes, and whether we accept or decline its loan is known as leaf. Depending on the attributes which can make more importance or not, we use the if else or else if algorithm to constructing these trees. So to understand how do we quantify or justify whether we are going to split in a tree, I'm going to give you a review of the entropy. The entropy concept originates from the thermodynamics, and it is used to describe the molecular disorder. In the information systems, Sherman's theory, information theory gives a concept of the entropies that it measures the average information content of the message. And it defines that the entropy is 0, 1, all messages are identical. And this when it is applied in the machine learning, entropy act as impurity measures. And we can see that as here, here is the formula to calculate the entropy, with the sum of the probability and times the weight of each component with the capital with the lowercase x. And here are the two examples. If we have an area with 4 parts, if they are equally distributed, and with each part it has a weight and a probability of 0.25, by using the formula here, we can calculate the entropy of this system is 2. And if the distributed of the 4 areas is not equal as shown here, with 3 parts has the area of 0.1 and 1 part with the area of 0.7, then the entropy calculated out is 1.357, which means the entropy of the right one is less than the entropy of the left one. That can be obviously observed in this simple case by just using the diagram, but in a more complicated case, when you have multiple attributes and different cases, it cannot be seen directly, but only be calculated with these entropy formulas. So now we know we have a review of the entropy concepts. And we also recall that we have another concept to measure whether we need to split the cheese or not. That is called Gini impurities. Somebody last time asked which one we need to choose. For most time, there's no difference between these two, but the default selection is Gini impurity due to it is faster to compute in some cases. But if you want to know in detail, that entropy tends to produce a slightly more balanced tree, while the Gini impurity will isolate the most frequent cards in its own branch of the tree. So now we know the concepts entropy. We want to review another concept we learned last week is called information gain and information ratio. When you split a cheese, you want to decrease the entropy. That's why we split the cheese to make a better classification. You want the entropy to be reduced, and then if that's you minus the entropy of the original cases by the new cases. If that value is a positive value, you have information gain. And in most of cases, we determine whether we want to split the tree or not, depends on the largest or highest information gain. But there's a problem that's when we considering which feature to choose for splitting the cheese, for example, the colors, or whether his whether his age is greater or smaller than 40, then the colors one has more features. For example, he has green, red, and black, and this will create more entropies than the just one single age, like greater or smaller than 40. However, in most cases, the great age may be more important than the colors. Therefore, another concept of information ratio is introduced to help reduce this kind of cases to correct. We want to select the feature to splitting the cheese with more importance than the feature with more variables. Now we have reviewed the descendant trees, review some concepts of the descendant tree. Let's talk about let's talk about the descendant tree construction. To determine whether we are going to further split or further construct the descendant tree, we have two basic cases. The first one is all sample in the samples in the list belongs to the same class. When this happens, it simply creates a leaf node for the decision tree saying to choose that class. That means if we got only one, like all the samples in this list saying we are going to decline the loan to this person, then we will not going to further split this decision tree. And the other cases is that none of the feature provides any information of the game. For example, when we come to a node, it says the color of this applicant's car. And no matter what colors it gives, it cannot give further information of whether the entropy will decrease or not. Then we will not going to further split on this case. So the algorithm based on these two base cases is that we first check for the base cases, and then for each attribute, for example, A, find the information gain or information gain ratio from splitting on A, then let A be the attributes with highest information gain or information gain ratio. Then based on this condition, we create a decision node that splits on A, and we recurse this process and on the sublist to obtain by splitting on A and add those nodes as children of node. So once we know the decision tree, and we use that as a base learner. However, we know that we don't fully understand the data structure. So the decision tree we first come out maybe have many disadvantage or have many defects. That's why we need to use the ensemble learning to combine different base learner or the learner we use, the learner use the decision tree we made, to combine them together to make a strong learner, and then provides us a improve output with improve efficiency and more accurate outputs that we want. That's the underlying principle of the ensemble learning. And there are two algorithms in the example. The first one is called bagging, as we last time learned. That bagging approach is to use the same chaining algorithm for every predictors and chain them on different random subsets of the training sets. When sampling is performed with the replacement, this method is called bagging, short of the bootstrap aggregation. So here is a diagram of what I said. From the training sets, we just use the bootstrap to construct a different training sample, training and test group. And then we use the same training algorithm for each training set, and then we get different predictors. After all the predictor is generated, we do aggregation or usually the average algorithm to make a new predictors, and then use that predictors to predict the new instance to generate a strong output or prediction. The other algorithm is called boosting, which is the main focus in this lecture. Boosting, originally called hypothesis boosting, refers to any ensemble method that can combine several weak learners into strong learners. The general idea of most boosting method is to train the predictors sequentially, each trying to correct its predecessors. So in this case, all the training data from our sample data is going to be trained through this training process. But compared with the bagging, it is now sequential. The first weak learner may produce some mispredict points. And in this case, I will use the adaptive boosting methods, which put more weight on the mispredicted concepts points. And then in the next training routes, we put more weight on that mispredicted points, and then we continue train that, and that will produce new misfit values. And then we will further put more weight on that and go on with this process, and then we can get a better training algorithm than the first training, as you may see here. And the other training boosting training algorithm is gradient boosting, which is to adding a weak learner to predict the loss function from the first, like for example, here we first use the weak trainer to train to get a first training line here, and then we calculate the loss function, and then we add another weak learner to predict the loss function, and then this will generate another loss function and further. And then at the end, we combine all these loss function, all these weak learner together, and to generate a better training algorithm to predict the to get better results. So here is a conclusion of the bagging versus boosting algorithm. The bagging is basically the parallel training algorithm, and the boosting is a sequential. Compared with the bagging, the boosting algorithm usually provide you a better or faster computing algorithm than the bagging in most cases. And as for the details of the boosting algorithm, my colleague Zoe and Liang will be further explain them to you in the next of the course.
Thank you so much, Wei, for the great presentation. And I'm gonna start my screen sharing here. Wei, could you stop sharing? Okay, I guess that everyone can see my screen right now. So my name's Zoe.
Actually, Zoe, I think like before your start, let's see if we have any questions from the audience.
Okay, sure.
Just on the first part. Sorry to cut you off. So comparing with bagging, is boosting more memory intensive? I think the question is the boosting, because it's sequential, is hard to parallel because like one needs to be built on top of another. But I think there are still ways to parallel them. And that's pretty much like the hardware acceleration work done by the XGBoost paper. Personally, I don't have a very depth understanding of like all the hardware accelerating techniques. But yeah, compared with bagging, I think boosting is hard to parallel. And in that sense, I think we can say it's like more memory intensive. Yeah, that's kind of like my 2 cents for that question. Anyone feel free to add anything else if you want. And also just before our next section, I just want to ask like the audience a quick question. Feel free to like type your answer in the chat box. The question is, can entropy be negative? If you still remember the formula. We have 1 no, if anyone else wants to participate. It's within the range 0 to 1, I assume that means. Yeah, so I think Connor gives a pretty good explanation because it's about probabilities And probabilities is always between 0 to 1. And then when we do the log, we bring the negative sign into the front. So that got canceled. So entropy can never be 0, but I think it can go beyond 1. So it can be like, say, 2 in the example that we showed. Yeah, I would just want to do a quick review just in case if you missed like a last great presentation, and I just want to make sure you're familiar with these concepts, and we'll talk about more about those. Sorry, Zoe, please go ahead.
It's okay. I'm gonna share my screen again.
Yeah.
Yes, so my name's Zoe. I'm a very recent Master of Engineering graduate from University of Toronto. I'm still learning this field, so I'm really happy to be here and share my 2 cents. So you could probably think of my presentation as a very short and soft introduction for Leon's part. So I'm just here to revise on a couple of really key ideas, and everyone just please bear with me and then listen through my presentation. I'm gonna try to make it as enjoyable as possible. So first thing that we want to look at is objective function and bias variance trade-off. So I think it's a very important key concept that the author of XGBoost, Tianqi Chen, actually emphasized a lot. The idea is that we want to have models that are predictive and also very simple. So when you look at the objective function, there are 2 really important components. The first one is the training loss, and the second one is regularization. And they control different parts, and they control the bias variance. So the training loss part measures how well the model fit on training data. And the regularization basically measures the complexity of a model. Why do we want to look at 2 key parts? It's because we can't only focus on one component of the objective function. So if we just look at training loss and we just want to minimize training loss as much as possible, we might have a very good performing model that gives you really good results. And you look at your training accuracy and you're like, okay, I'm done. However, it's not actually the case because we have a low bias model. However, we have really high variance, and it's really difficult to generalize on the other data that we've never seen before. So it's actually not a very good idea to only look at the training loss. So we have regularization components, either lasso or ridge or other stuff, to help us with making the model simpler from the previous very complex model. So we want to have a more stable prediction on the data that we've never seen. So it's really important to have this trade-off between bias and variance, because we cannot make both parts really like perfect. We can only do the trade-off. So bearing this thing in mind, let's revise on the tree-based methods together too. So I borrowed 2 very good looking slides from Professor Alexandra Chaldachova. I'm hoping I'm pronouncing it right, from CMU. So we've learned that tree-based methods operate by dividing the feature space into rectangles, meaning that the tree-based methods are not linear. And each rectangle is like a neighborhood in a nearest neighbors method. So you predict, or here we can actually understand it as regress, using the average, or classify using the most common class in each rectangle. And the good thing about tree-based methods is that it can handle numeric, categorical, ranking data, and it can also handle a lot of missing data. So it's really great. And the thing that we need to remind us is that decision trees basically is just a series of if-else statements. And we use this to predict data within our data set. So when we look at the tree-based methods, we can see that here it's basically just putting data into different neighborhoods, into those rectangles. And the trees are built up via a greedy algorithm called recursive binary partitioning. So at each step, you would pick a new split by finding the input x sub j and split point x sub j that best partitions the data. So in regression, you would choose splits to minimize the residual sum of squares. And in classification, you would choose splits to maximize the node parity. In many cases, minimize the Gini index, which I think Wei has already covered. So let's talk about regression trees, because regression trees are like the foundation where XGBoost is built on. So the thing that we want to memorize is that we want to look at the leaf nodes, and there's always a value assigned to this leaf node. For example, we have an example here where you have a lot of people data points, including age, gender, occupation, and then we would want to split on, for example, age, and then if this person is male or female. And then at each leaf node, we actually have a prediction score for each leaf node. And the thing with those scores is that it's really important when it comes to regression tree ensemble, because we're basically just putting those numbers together, putting the different prediction scores for each data point from each regression tree and then summing them up. So as you can see here, this little boy, if we have only two tree classifiers, the idea in this ensemble is just we want to have this prediction score of the two scores in each regression tree summed up. So here it's just 2.9, which is 2 plus 0.9. So prediction is sum of scores predicted by each of the tree. And now, since we have an example of regression trees, we are actually looking at y hat as the summation of the scores for this data point regress from each of the trees. So we can say that f sub k is actually from a space of functions containing all possible regression trees. And we're basically summing them up together for each of the scores for this data point, and then getting the yi hat, which is basically the prediction for this data point. So we can think of regression tree as a function that maps the attributes to the score, and then we're just summing up the function's scores. So we can look at the parameters in different ways. For example, we could look at those parameters for predicting yi hat as potentially the different splitting points or the different scores within each leaf node. But we could also look at it in this way. We could think of the parameters as just these functions, and those functions are just regression trees that we have seen before, right? So here we're no longer looking at features and weighting those features. We're actually learning the functions. So that this is a different change of mindset when we're learning about regression tree ensemble. So how do we learn functions? First, and it's very clear that we have to define objectives that contains loss and regularization, and then we want to optimize it. So let's just take me as an example. So here we have something, we have this target of looking at the variable time and then predict whether I like romantic music at time t. I don't want to offend anyone, so I'll just take myself as an example. So the model is just a regression tree that splits on time, which is very intuitive. And the idea here is that we want to look at this regression tree as a piecewise step function over time. So script the boy, this is just me. And my rate over love songs before I met my boyfriend is potentially really low. And then afterwards, we could see like here, there's a time period which I have a really high love for romantic songs because this is the honeymoon phase. And then afterwards, after this time splitting point, we're looking at potentially a drop in the score or maybe a jump in the score. You can't guarantee for sure. But the thing is, there's this splitting point in time and there's a score tied to this time period. That's very important. So as I said before, we want to look at the single function with two things in mind. The first thing is the splitting positions. And the second thing is the height in each segment, which is basically the prediction score for each leaf node. And why is this so important? Because this ties back to the bias variance trade-off that we mentioned again and again. So just take a look at the model, take a look at the objective, and then think like, why is this important? We have a very intuitive figure from Tianqi Chen's slide. So let's just see, we have a user interest via time regression tree. And then the goal is to have a very good balance of training loss and regularization, which is a very good balance of bias and variance. So the thing is, if we're having too many splitting points, one of the factors that we mentioned before, if we're having too many splitting points, we have really great, we have really tiny training loss, which means we have a really great performing model that has really low bias. However, it's overfitting on the data. So as you can see, like the variance is really high. We don't want that. So we don't want too many splits. We want to be very mindful of how many splits we put in a regression tree. The other thing that we're very mindful of is the scores. So we don't want to split when there's no difference in the score and basically causing a wrong split point and causing a very high bias in our model. So we want to have this split exactly at the place where the score is making a huge difference. So we could eventually bring those two things in mind, have a very good balance of bias and variance. And this wraps up my part for the presentation. And I'm gonna hand it over to Leon to tell us more about gradient boosting and XGBoost. Thank you.
Thank you, Zoe. That was a great intro on the regression tree. Anyone has any questions? This is going faster than I thought. Share my screen. I'm finding the chat. There you go. With time, what is the best way to balance bias and accuracy? I guess the best way is very hard to find. We just build those considerations into our objectives and hope that we can optimize on both of these directions, and in order to achieve some sort of local or global minimum. I don't know what is the best way I think because it's some a convex optimization problem, so there's no guarantee for the best. So it's just the best thing that we can do. With time on x-axis, how realistic is it to choose splits ahead of time? With time on x-axis, how realistic is to choose splits ahead of time forecasting? Can you elaborate on that a little bit? So the x is a time input.
Yeah, so
choose splits
on the x-axis, and I'm just wondering if you're trying to predict a year ahead, how would you know the specific date to split it on that's going to increase y by a significant amount?
I see. So as you probably already know, for time series, there are a whole different set of algorithms that you can do. Mm-hmm. Say a RIMA or LSTM. We can use XGBoost, but then we kind of need to define something to be able to apply XGBoost properly, such as a rolling window or some other stuff. So I don't think you need to do splits ahead of time. It's more when you do the prediction, you just predict day by day till the day that you want to stop. Right? So you only do splits in training, but then while actually testing, I don't think you need to do split. And the split will be on the non-time inputs. You can based on the time information, you can do some inference on some of the features and then use those as input. But yeah, I mean, using XGBoost on time series I think it's a pretty different topic, and I don't have like a lot of understanding on like the tricks applied there. I'm more familiar with like using XGBoost on just like the traditional tablet format. Sorry about that.
But with time series, you probably wouldn't be as competitive with the other more models like ARIMA or linear regression if you're doing a time series.
Yeah, I mean, time series like ARIMA works pretty well. There's so many other time series algorithms. LSTM works pretty well. I mean, using XBoost, we just need to find some like proxies, and we kind of need to define our time window, and then kind of like reconstruct from like a time series into like a non-time series kind of like input, which is like encode the time information in somewhere. That's something that we tried and worked, but I'm not sure that's like the best way to sort like a time series problem.
Okay, thank you. That makes sense.
No problem. Thanks for the question. All right, so without further questions, yeah, please keep those questions coming. And for the next part, we will talk about the math, some of the math behind the gradient boosting algorithms. Yeah, my laptop is surprisingly slow today. I close everything that I can close. I just don't know why it's so slow. I cannot see my cursor moving. Let's see. So I tried to download a PDF version of the presentation. Let's see if that is working. No. Okay, I think I have to present using this view. Hopefully that's okay. So the motivation of talking about the details behind, like you can use XGBoost, use scikit-learn XGBoost or XGBoost itself without knowing like this kind of stuff. But I still think it's like fun and satisfactory to know the details behind. I think curiosity is very important as a part of like a data scientist. And also, let's face the fact that you need to talk about these kind of like a level of details for the models during like say job interviews or when you need to impress your colleagues at work. You cannot just say, oh, I just tuned the model, right? So I just tuned the model using like 2 for loops doing random search research. So you need to talk about the details. And also I kind of want to say, I'm not very good at math myself, but like I can understand most of this stuff. So I'm pretty sure you can as well. So hopefully I'll go pretty slow in each slide and make sure you can also understand like all these kind of like things behind. If you have any questions, please don't hesitate to ask. Okay. So also lots of the content in the stack, they are borrowed or copy pasted from the XGBoost author Tianqi's slide. And also in the XGBoost, like the official documentation, they have a very good like coverage on some of this stuff as well. So if you want to like find some other like things to reference, feel free to go to either the original paper, which I linked later, the PowerPoint from like the original author or their official document. So I just want to talk about this slide again, because I really think this is the fundamental theory or fundamental like philosophy behind like so many different kinds of like a machine learning models, no matter if it's like a random forest, XGBoost, or a logistic regression. All we want to do is we want to use math to construct a system that we can somehow calculate this like objective function, OBJ, theta. Theta means the parameters of the system. And then this objective function, just like milling, contains 2 parts. One is the left part L, which is the loss. And then the right part is omega, which is the regularization. So loss defines how close your predictions are towards like say the targets in your like supervised learning setup, the target variables. And omega determines like say how complex the model, your model is. Usually we say like if the bias, if the variance is too high, that means overfitting. So it means like the complexity of the model is too high, so it won't do a good job in generalizing to unseen data, right? So we want to be able to train a model that can perform well on the data haven't seen so far. So we want to control the regularization for that purpose. And a couple of things, like when we need to find some like a concrete idea of the loss and the regularization. For loss, I think you're probably already familiar with the square loss, right? So you just like find the y bar here is the predict result from like each single instance I. We say there are n different instances in our training data, could be an Excel, could be a data frame for pandas, and it's from like I equals to 1 to n. So y bar is the prediction on the instance. Y minus y bar means the difference from our prediction to the y true, which is like what is given in the data set. And we square it. So like they won't cancel each other, and we kind of like finding the cumulative loss using this sigma thing putting at the front. And then we say this is the total loss for a function. And the goal again is to minimize this loss, right? Is to minimize this. And the regularization, regularization is a term that I had trouble understanding with when I started to learn machine learning. I just don't understand why it exists there. But then if we think it a little bit through using this function, and we see how the normalizations are usually defined, we see either it's like a L1 norm or L2 norm. They are both like either way, this number will always be positive. And this L2 norm or L1 norm is determined by the weights, right? So the weights is like, if you think about logistic regression or linear regression, weights are like what's the scaling factor of your like input parameter. And by putting this, either we sum of them up on their absolute values or square and sum them up, by putting this into the objective functions, it means if the weights itself grows too big, like say 100, then this objective loss, like this objective function cannot be too small, right? Because this is like a absolute positive number we're applying here. So by doing this, putting omega theta, and the theta depends on W, forces us to find smaller and smaller weights, and can also give us a similar level of performance, right? So that's the purpose of like a regularization here. Maybe I'll pause here and ask a question. What's the difference between L2 and the L1 norm? If anyone wants to talk about that.
I think it's just a calculation, in which I think L1, I think it's just the subtraction, and L2 norm has to do with the subtraction squared.
Mm-hmm. Yeah, so calculation is definitely different. Thank you for opening up your mic, and I really appreciate it. So the calculation difference also causes like these two norms to have different like kind of like a feasible domain of finding the possible solutions. So you might probably know. How about I ask it in another way? If I want to, let's just say, what's it called? I want to do feature selection by using some of these regularizers. Which one should I use? Okay, I see a couple L1s. Anyone think it should be L2? And anyone wants to give an explanation why we want to use L1 for feature selection? Probably no. Yeah, so basically it's related with like the feasible domain that we talked about, right? So I mean, this is not related with XGBoost, but then R1 itself is like, it's a square if we put it into 2D, and the only possible answer that you can find are on the axis, so which forces the other value to go to 0. So if you want, you can search that up, just Google it. But like, yeah, so different ways to formulate the different like norms kind of have like a more practical meanings. So, but either way, both of these will like force our weights to be in like a smaller range compared with like without the norms. So yeah, that's I want to talk about for this page. Next slide. So how it learns. So here in XGBoost or gradient boosting, the objective function, what we just talked about here, this part, has been rewritten into this format. So a similar idea from I to 1 to n, for looping through all the instances. And we find the loss, which is the difference between our prediction result and then the target value. And this part is the regularization part. We haven't looked into how to formally define these like terms yet. This is just like, we're going from top to bottom, trying to understand the high level picture first, and then we like precisely define what kind of like equations or formulas that we want to give for each of the component. And here we see we have another sigma here, which is like over k. K is the number of trees that we define. So if you still recall what we talked about, like about the boosting algorithm. So we have like a different weak learners, each tree built one on top of each other. So that's the number of trees that we have. And that's omega just means like we want to penalize like if we have so many trees constructed, because we think about like, say, if we build up 1 million trees to solve a problem, that means like this model has a too high complexity. So we don't want to do that. So we kind of factor that term in here. So we try to like keep our objective low. Like we also try to use less number of trees to solve a problem. And the difference between this function in a tree-based method versus like, say, linear regression and logistic regression is like, on like linear regression, you can use things like stochastic gradient descent, which is this SGD, to optimize the vectors of the weights, right? So that is something that has been proven to be very helpful and useful, and it works. But here we're talking about trees. So we don't have such a like a convenient like tool or method to use. So we need to find another way to like gradually like approximating towards like the solution that we want to find. And the solution from the author is called additive training, which also referred as boosting. So for boosting, again, high levelly, for all the predict results at the beginning, here the 0 means like it's a time step. So we start from 0 towards like time t. And up front, we just set every prediction to be 0. And that's our first prediction. And apparently that would be wrong. And then the next step, we will just use, we will find like F1. F1 means the tree that we construct at this time step 1. And it takes an input of xi. Xi is the ith element of the input. And then what is F1 taking this input? So we're talking about it needs to be built on top of like what we had before. So it needs, so it equals to what we predicted in the last step plus this new tree result, like new tree that we constructed on this instance. And this is only on one row of the data set that we got, right? So, and this, we haven't formally defined how to make this tree yet, but just like, I hope you can already have the idea. I think this picture is very self-explanatory. is like every time it builds on top of like the previous step, right? So it's not parallel like bagging. It's like every step is like using the result from the previous step. So the previous step will be contributing into the next step. All right, so that's the high level idea of how we approximating towards like the ideal solution that we want to find. Any questions so far? Okay, if not, let's proceed. So now you know, like each step, we will find a new value, like a new predict value for this like input instance. And we need to know, like we need to optimize this objective. So like we need to have a way to evaluate what kind of like predict result is better. And we need to have a way to stop, like we keep iterating. And after a certain point, we say, okay, this is pretty good result and we can stop. So the next couple slides will be talking about how do we evaluate this like predict result, and then how do we optimize this objective. So we already know at run T, the prediction is defined in this way. So previous result plus this current run. This is like a new tree that we propose at this step. And then going forward, so the objective, if you still remember, it is defined by the loss plus the regularization. And we want to expand this loss a little bit. We want to count the previous run and the current run. And we kind of want to know, like say, what's the gain of like constructing this new tree. So to put that kind of like idea into our objective functions, so the loss function has been rewritten into the yi is still like what we had, what is given, our true label. And then this new prediction yit, we just use this formula here. And now the loss function is we try to find the difference between the true label and this round of prediction. And we still add the regularization term and some of the constant say, okay, I don't want to, because like each time if we build another tree, we think this is adding a complexity. So we use a constant to say this is the penalty of like making a new tree. So these, ignore these parts. So don't worry about these parts. So we just focus on this part for now. And if this is like too abstract, we can think about like the squared loss. So if we have a squared loss, it's chosen at every step to minimize. Yes, we can loop back to that later. So the square loss is like yi minus like the predict result and squared, right? So this is just like a mean square loss that everyone probably is familiar with. So this is the square loss, and if we expand this function, like note this yi because this is given, and this number will not change between round to round because yi doesn't change. So we can just like drop this term. And also constant, we can drop them if we talk about like we want to minimize something. So we just drop the constant term because they don't affect our minimization goal. And we expand that, we can rewritten this formula in a way like this. So if you want, you can do it like by hand afterwards. But like, yeah, just this is like after the expansion of this formula, you get this. So the question is, so ftxi is chosen at every step to minimize the objective function. I think ft is the tree model at run t. So I think both are correct. So ft is the tree, and this tree needs to be constructed in a way so the overall objective is minimizing, right? So I think both are correct. All right, moving forward. And before keeps talking about like how do we do the approximating, we need to borrow an idea from math, which is called Taylor series or Taylor expansion. I think Taylor expansion, this is the Wikipedia definition of Taylor expansion. I prefer, like, in layman's term, this means like we know we have a function that we don't know, like, say, how complex the function is, but Taylor series or expansion gives us a tool to approximating, like, towards that function, and by gradually using the derivative information at each step. So this may look a little bit abstract. Let's if you're using slide, you can refer to the video I put here. 3 Blue, 1 Brown is my favorite, like, YouTuber on math. So if you want to look at their explanation, please do that. It's gonna help you understand this idea much better. But, like, in short term, what it means is, like, this blue line, this blue curve is the sine function, but we don't know it's a sine function. And we want to find a way to, say, approximate, like, find, like, our own function that can fit towards this, like, blue unknown function. So the way to do that is by defining a function at some point, and then gradually using the partial derivative information. No, just the derivative, not partial derivative. Using the derivative information, just like the higher and higher orders, and then translate those information into how should we change, like, say, the slope, the curvy, and how we can get these two lines closer to each other step by step. So what I want to convey here is, like, this blue line can be some, like, high level function of the ideal solution for the XGBoost problem that we want to solve. And what we're trying to do here, we start with a very simple term, which is basically like the constant, and we gradually build on top, like, of each other to approximate to that complexity. And then by doing this, like this approach, we are trying to get, like, our proposed solution on the similar level of complexity of this, like, actually, like, the solution space or complexity. And this is the idea that we use in our XGBoost, like, gradient boost algorithm to approximate to the answer. So formally borrow the idea of Taylor expansion. So here we have the goal of this again, and then using Taylor expansion in mathematical terms, we can think of, like, say, we have a function and we have a delta x, and the way that we can like approximate to this delta x is by like gradually increasing, like, the derivative information and, like, doing this kind of like approximation. And here, this is the Taylor expansion that we just saw. And then here, the first, like, derivative function, we define this as gi, which is the derivative. This is the partial derivative of y bar t minus 1, which is our previous round of prediction. And this, like, second order derivative, we define it as hi. Is also the second order of the partial derivative of y bar t minus 1. And you can think of, like, this derivative is on the like the tree. No, this is just on the prediction of the previous round. So gi and hi are just like these two new variables that we introduce to capture this, like, derivative information that will help us approximating towards the solution that we want to find. And now this objective function with these new introduced variables can be rewritten in this way. So this way, let's read this through from left to right. So now instead of, like, equal, we are saying we're approximating, and still from, like, a looping from, like, a 1 to n. And the loss is, like, we keep the loss the same. So this loss is defined by our previous step prediction and the given result, plus this new GI on the FT. FT is this new tree that we construct in this round, and also the 1/2 of HI, which is the second order derivative information of, again, this round of the tree. And then we plus like the regularization term and the constant. So here you notice like for this FT, because the goal is to minimizing this. So basically we're saying, as long as you are minimizing these, the whole objective will be minimized. And you can see this, you can see why this is true by going through this YouTube video that I posted here. So anyways, now we kind of like redefine the objective function from this format into this format. And yeah, if you're not comfortable with like looking at these variables, think about like what GI means, right? So GI is calculatable. It's calculable because like what it does is just to, if we think about this as like a square loss, the partial derivative information, you bring this 2 at the front, and then like there's no coefficient to the y bar t minus 1, so you just multiply by 1, and this is like how you calculate your GI, and you have yi already, and you know what is your predicted like result for the previous round, so you can find the value for GI using square loss. Similarly for HI, doing like 2 times of the derivatives is just like a constant 2. So if you're unfamiliar with this number, you can think of this as like 1/2 times 2, which makes this 1. And this is like basically this. Okay, I think this is a good time to pause and see if anyone has any questions. If not, I think we can take 5 minutes break. If you want to skim through this video, feel free to do so as well. Any part that you want me to repeat?
I think in Logan we can take 5 minutes break, and people may have some questions after the break.
Yeah, sounds good. All right. The prediction score in the regression tree. We have a score to evaluate the tree, so we'll talk about that in the next couple slides. And the prediction result is just whatever we are trying to predict for, what we are regressioning for. So if it's classification, then we kind of need to converge from that result to some probabilities. But yeah, let me know if you need more explanation on any of those scores. All right, should we keep going, or is everyone lost? All right, so yeah, I think it's totally okay if this part confuses you. You can figure out like these later, but I think what's important to know at this step is now we have redefined our objective function from this into this. So this is our new goal. So in our new goal, we are dropping all the constants because we are minimizing it. We only want to take a look at the things that may change step after step. So we are just dropping all the constants from this formula. So this loss, like because this is already a last step, so this cannot be changed. We drop this, and we just like ignore these parts for now as well. And our new goal is this like derivative information, first order, second order, and complexity, because we still want to penalizing the tree for like for making new trees. So the complexity will be factored into our optimization goal. right, so I guess, yeah, why spending so much effort to derive the objective? Why not just grow trees? I think the author gives very good explanation on the motivation. So we want to understand the theory. We want to know what we are learning. What is the condition of convergence, and also it also has like an engineering benefit. So if you need to, well, I never implement my own XGBoost, but if you need to implement XGBoost, you can further modularize different components after fully understanding how parts are working with each other, right? So like you can now, with a better understanding of like each step, what is the actual like things that we're looking at, you may be able to better define the classes, better define the functions, and then put them together into an algorithm. So, but like, yeah, this is our goal now. And now we haven't talked about, like, say, how to find FT yet. So how to construct a tree, and what kind of tree is a good tree. We haven't talked about that yet. This is all about, like, say, now we have an objective, and by keep pursuing like a lower and lower value on this objective, this is like what we want to do to find the most optimized solution. So now we'll talk about, like, say, how we can define the tree, so we can find a way to construct them. So we define trees by using vectors to represent like each tree, and it has two parts. One part is the vector W, which contains like the leaf weights of the tree. So so here, this W in this example, if you still remember, we have some family members, and we want to see, like, say, who use computer for long times and stuff. So these weights, leaf 1, leaf 2, and leaf 3 are the end nodes, which are the leaves, and each leaf is associated with a weight. So this is +2, this is 0.1, and this W3 is -1. And these are the results from this tree, the predicted results. Let me see this question. Is the derived objective for all types of boosting methods or just for XGBoost? This is for gradient boosting. So GBM, to be more precise, I think. XGBoost is something built on top of GBM. XGBoost uses GBM, but I don't think GBM considers the regularization term. So I think that's one novelty that XGBoost proposes. And the other things are just on how to handle all the edge cases. And also it proposes several ways to faster construct a tree. But then the overall idea is the same. Like the objective function is the same. Just like it's faster for XGBoost. All right, so the weights, W is a vector, and we can think about like putting these three numbers in a vector, and this is W. And also we have Q. Q is the structure of the tree, means it takes like the input as a variable, and then the predict result is like which leaf that this instance will belong to. So here we say Q, and the input is boy, and then we say this is leaf 1. So the first leaf, that's why this is 1. And the Q grandma, she falls into the third leaf. So Q grandma is 3. And yeah, so this is W and this Q. Q is you can think of Q as a function. It's a structure of the tree. So by redefining like the tree into like using W and Q to represent a tree, we use this way to kind of like guide us how to find like a good structure for the trees. All right, so now we'll talk about this omega thing that has been like We have been seeing it like since the beginning, and now we'll give it a formal definition of this omega. So omega is the complexity, and the complexity of a tree is like omega takes a tree as a variable, and then the result is determined by like these factors. So first thing is gamma. Gamma is just like something you define in when you call the method. So this is like one of the hyperparameters that you can tune. And T is a number of leaves, as what you just saw here. T equals 3. We have like 3 leaves. Yeah, also same thing here. We have 3 leaves. 1/2 plus this is lambda. Lambda is also a penalty. It's a penalty for the weights, and also this is like when we talk about like say the L1 or L2 norm, we don't want the weights to be like say 10,000 or like or even bigger, right? So if you are familiar with linear regression, if you don't use ridge or lasso, you have some good results, but then the coefficients just like off the chart. It could be like 10,000 or like even higher. But putting like the regularizations, they are like between like say -1 to +1, which are good to interpret. And here a similar idea. We have like the weights for each leaf putting here. So we don't want the leaves to be too crazy. We want to make the weights or the output of leaves in a reasonable range. So by giving this like a formal definition of omega and taking this example, let's see how we can calculate omega. So we have three leaves. So it's gonna be 3 gamma plus 1/2 times lambda, which is another hyperparameter. And then the weights is like wj squared, right? So this 2 squared is 4, 0.1 squared is 0.01, -1 squared is 1. So by doing this together, we know that for each step after we have the prediction results of a tree, we can calculate this omega value using like number of leaves, the weights, and we can find omega. Any questions so far on these 2 slides? All right, let's continue. So now, again, we can revisit like our objectives after we have a better understanding of the omega here. Just one thing is we redefine the instance. We instead of like looping through all different instances, like from 1 to n, we now put them into like the set within that leaf. So here you see there are 5 like instances, 1, 2, 3, 4, 5, and then we don't want to calculate it in that way. We want to calculate it in terms of like how many leaves that we have in this run. So here we have 3 leaves. So 1, 2, 3 leaves. So for each leaf, we called it I. So I is just the instance set in leaf J. And then again, we will rewrite our objective function again. So this is what we had before. And this is like just expanding this omega by what we just saw in the previous slide. And here in this last function, this like code the official documentation, this is where the magic happens. So basically this part, we are considering both like each round of I, we're considering each round, each instance side of I looping through each leaf, and then rewritten them, because like in the end, when we make predictions, we look at the leaves, not each instance. So we just like by grouping them, we rewrite like this formula into this formula. So let me see. So this part, I think we just factored some of the parts here and then regrouping them. And here we have our new objective function. And the reason why we want to redefine it again is in the next slide, you will see by doing this, it gives us this like a nice quality, nice characteristic of like this whole function is just a sum of t independent quadratic functions. And for quadratic functions, it has like good properties of like say, it can be easily find a minimum or maximum. We are very familiar with like what does the first derivative information mean in in quadratic function, and what does the second order derivative mean. So by regrouping all these into this form, and we can find the score to evaluate the structure of a tree. So just before we dive into this part, so the author is very thorough and tell us some like good like facts about single variable quadratic function. So what it's saying is like you can think of this g and h. So this g and h is just before just our like derivative information, first order, second order, and instead of like writing them in small way, we group them into this like a big G and H. But again, G and H, you can calculate them. So you can think of them as some coefficients. And if it's like something x plus 1/2 something x squared, the minimum of x is, you can find it by, it's just like a negative G over H. And when H is greater than 0 means the second order derivative is greater than 0, it is a local, it is a minimum. And the value of that minimum can be found by just like substitute this value back in, and this is the local minimum that you can get. So to make this easier to understand, let me see if I can find something. So here it is online calculator that you can draw a graph. So if we say y equals, we say x plus 1/2 x squared, you can see this is basically what we just talked about, the h and the g. And we say h is equals to 1 and g equals to 1 as well. And this is the graph that you get. And you know this is like, it's a quadratic function, and the second order, when the second order derivative is positive, it is like a minimum. So, and this minimum can be easily found by just like setting the first order derivative into 0, and you can basically calculate this number, right? So you can just like think about this idea when you think about this. So basically, after G and H are calculated, you can easily find like the compute like the minimum score at that moment. So yeah, here it's just like for each of the instance set small g, we just group them using this big G, small h, group them by this big H. And then by substituting this information here, we rewrite the objective function in this format. And this format, wj and wj squared, is basically what we just draw is the x. And then these, the things in front of them are just coefficients. So by using what we just saw, we know the structure of the tree, when it is fixed, the optimum weight in each leaf is calculatable. So the structure of the tree is fixed, the optimum weight in each leaf, and the resulting objective value is just like, this is the minimum of the objective value that we are pursuing for. And this is calculatable. And this score is the score that we use to evaluate the structure of the tree. I think this is a pretty big slide. Just pause here and see if we have any questions.
Logan, when you mean instance, is each instance a row of data?
So sorry, I think I used that word a bit vague. So let's say when we have an input, so each row is an entry, and here the instance is the leaf instance here. So it's like a leaf. It could be only contain one entry or like multiple entries in a leaf.
And in the algorithm, when we set up the minimum leaves number, would that affect the calculation there?
Yes, it will. But here we didn't talk about the like say how setting those parameters will change, like how these things will be like calculated. Here we're just assuming in the just assuming we don't have any libraries yet. We are trying to event XGBoost, and this is the thinking process of like how we do this. And then later, after we have this model working, and then we put them into a library, and then we introducing those like additional parameters. And those parameters will basically say, if you don't allow only one instance in one leaf, this node will not be constructed. So maybe this tree, like this branch will not be constructed. So it will just stop here, things like those. So, but yeah, but those are some like external factors that we don't consider them right now.
Okay, thank you.
No problem. Yeah, hope you kind of understand what we were doing here. So basically here, like after all the like 20 slides probably we have gone so far, we find a way to measure the quality of a tree, just because like this number can be calculated, you know, like basically that's the best that we can do given the structure of the tree and the optimum weight in each leaf. So like that's probably the there's something that we know like we cannot do better than that score, and that score is like defined by this value. All right, keep going. So we just want to show that like this value can be found, like maybe the thinking process is a little bit like daunting, but then to find this number is actually very straightforward. So like I say this is like a one of the time step, and for each node that we have like some leaves, and in each leaf, because like this I you know, we can group them together. So we have 3 leaves. So we have 3 I1, I2, and I3. And then this number is just like which entry or which instance from the input. So I1 only contains the first row, I2 contains the 4th row, I3 contains the rest of the rows. And then for each leaf, the G and H can also be found by just like doing the first order derivatives and the second order derivatives. So after these values can be calculated, you can just like substitute like those numbers into this function, and then you can get the like objective function score of this tree. And then the smaller the score is, the better the tree structure it is. So this gives us a tool to evaluate, like say, given 2 trees and like their leaves values and their previous like predictions, you basically have a way to tell which tree is better than the other. So that's all we got from like the slides before. Okay, so far we have a way to evaluate the trees. Now the next step is to figure out how to construct a tree, because like knowing how to evaluate them doesn't mean that we know how to construct them. So the naive way would be for all the possible tree structures, right? So when we talk about tree structures, we have different features, and we have like the decision tree kind of like structure. Like for all different structures, all different like features, we can just like enumerate like all possible combinations, and then for each like permutation or for each way of constructing the tree, now we have a formula to calculate the score. And then if we can loop them through and then find the minimum score, it could work, right? So that's the naive solution of the searching algorithm for a single tree. But as you probably already know, this naive solution wouldn't like scale up very well, just because like there might be too many features. Some of the features might be very sparse, so it's going to take infinite time to enumerate all the possible solutions. So the way to mitigate this issue is by using a algorithm to learn which is a good part to make the split. And actually, this part is more complex in the original paper because they had made like a couple contributions on like the novel ways of doing splittings, some quantile-based splitting, some like sparse aware splitting. So in practical, there is like way more details than what we just like gonna introduce here. But then just like this is like the method that is better than the like naive method that we just talked about. But like, yeah, just in reality, it's more complicated. So here we want to propose a method called greedy learning of the tree. So by greedy learning means like, so when we do a split, basically we are dividing this like feature that we're currently looking at into two parts, the left part and the right part. So the left part and the right part, because now we have a way to evaluate like the tree. So after we can just like propose a splitting point and then pretend that we do the split, and then we can calculate the new score of the tree. And then we just like calculate the left part, calculate the right part, put them together. So this will be the new score. And then we want to minus this old tree, like say if we don't split, what would be the score? And then we want to minus another constant to punish like for making a new split, because we are making this model more complicated. So by doing this, we can calculating like whether it's worth or not to do this like splitting at this particular point. So this gives us a way of like evaluating the splitting before the whole tree is constructed. So in this way, we say, if we do the split, and this split will give us a good gain, and then we will just like go for it. So it's a greedy algorithm. So greedy algorithm means it can only guarantee for the maximum maximum gain at the current step. It cannot guarantee like the maximum gain in the long terms, but practically it works pretty well. So this is like how we evaluate when is a good time to do a split of the tree. Yeah, maybe I'll pause here, ask another question. Is gain, like this gain, should it be positive or negative? Like say if we want to do a split, should this gain be positive or negative? Positive? Yeah, anyone else wants to take a guess? Yeah, so it should be positive because we're talking about gain, and if we work out like the formulas, we substitute here, because the way is like finding the minimum. We want to minimizing something, and then there is some like a sign reversing here. So this new split should give us like a smaller value, and then reverse it is like a bigger value. So the gain is positive, but also from the name gain, you can also tell this is a positive thing that we want to get. So so here it's the same idea. So we talk about like the gain of split at this point A. So here what we say is like for the same example that we have been used, we assume this is age. How do you allocate the instance indexes? How do you allocate the instance indexes? What do you mean by how to allocate? So if it's a tree, then based on these, how do I define? Like say there's like I1, I2, I3, like the indices of these, like I think here it's just like from left to right and one by one. And then the elements it contains, it's a set of the instances that like belongs to this set, right? So this one is just like this row 1, this 4 is just this row 4. This I3 is just like row 2, 3, 5. And this index, I don't think it means anything. You can define the way that you want as long as you keep tracking them. I don't know if that answers your questions. If not, yeah, please let me know. So here we have the age of these examples. So we just sort them from like the lowest to highest. And then here we just propose a split. We call this split A. And then this split A will divide this feature into 2 sets, right? Basically the left part of the tree and the right part of the tree. So, and all we need to do is just like substituting the G and H into this, and then we can figure out the gain. So the author says left to right linear scan over sorted instance is enough to decide the best split along the feature. So yeah, it's a greedy algorithm. It only looks at this feature and then do a splitting and use this gain to find which is the best location to do this split A. All right, so this, I think it's just a summary of this like split finding algorithm. So for each node, enumerate overall features. For each feature, sorted the instances by feature value, use a linear scan to decide the best split along that feature, and then take the best split solution along all the features. So this basically tells us, like say, how is this is male node getting constructed, and also I think this is binary. So this binary we don't have, we don't need to do the linear scan. But then if this is age, like say age less than 15, and also how is this 15 getting decided? So this algorithm helps us to define both of those information. And the time complexity growing a tree of depth k is like this. I haven't like read through like these details, but if you're curious, you can read it through. So basically the conclusion is like this is a pretty optimized way, and then it can scale to very large data sets. And if like the value is not like say something like age, where you can sort them from lowest to highest, if it's like say categorical, other than like the other kinds of like tree learning algorithms, like that which they need to handle the category variable and continuous variable separately. Here, the XGBoost is kind of like aware of the of this like categorical issue. So like when we handle categorical values, sometimes we do one-hot encodings, and then if the value has like a lot of like different variations, the feature can become very sparse. So there is a particular section in the paper that says they have a algorithm to handle the sparseness So it's called sparse aware splitting. So if you're curious, sparsely aware split findings. So this is like how they particularly optimized for this issue. So if you're curious, you can read this part. All right, so next part is the pruning and regularization. So pruning and regularization, I think we talked about like regularization a little bit. We haven't talked about pruning so far. So pruning means like we want to modify the tree structure after the like say the model finishes like training and we have a pretty stable set of trees as our solutions. So here there are two types like a pruning that we can do. One is called pre-stopping. Examples including stop split if the best split have negative gain. So if that's the case, then we just like do not split anymore. But like here, the problem is maybe a split can benefit future splits because again, this is a greedy algorithm. So maybe the best split gives us like say -2, which is a negative gain, and we want to stop. But maybe from this -2, the next step that we can have like a big gain, like 10. So it's possible. So this is the risk of using pre-stopping. So I guess this will be depending on the context, depending on the task that you work on. And then there's another type of pruning called post-pruning. So we just first grow a tree to the maximum depth that we define. Usually, I think in XGBoost, it should be like around like 3 to 6 or 3 to 8, which should be smaller tree because each tree should be a weak learner and it's additive like on top of the others. Instead of like say random forest, you have like the base learners are trees and like maybe like a much deeper. And then after the trees grow to the maximum depth, we recursively prune all the leaf splits that has a negative gain. So practically, I have never done like post pruning before, and also I think I'm not sure if this is a part like built in as a part of like the library of XGBoost. So if somebody knows, please send them in the chat. And also for the regularization, we talk about those. So when the training loss reduction is smaller than regularization, which is this like constant that we have been introducing at the beginning, we basically say this is not a good gain. We are making this model more complicated, but for a very small benefit. So maybe that's the point that we should stop splitting. So all these kind of like strategies on what's the best way to stop early or stop late or modify the structures are called like a pruning of the trees. So recap, boosted tree algorithm. So we add a new tree in each iteration. And at the beginning of each iteration, from the last tree, we can calculate the first order derivative of the loss, and then the second order derivative of the loss. And we use those to calculate like the gain of this new tree that we proposed at t time ft, and then this will give us the objective like score, and the goal is to find like as lower objective score as possible. And if like the gain is good, we add this ftx to the model. This is our new prediction. But usually we don't like to get the value, we use this like parameter called learning rate, which is the same to like say stochastic gradient descent or the other models. We don't want to just like add the full like new scores on top of the previous score. We want to discount it because we want to leave some room for the future ways of like growing trees, and we want to prevent overfitting. So this is like the boosted tree algorithm. Another summary, and I think the most important part is still this part. So this kind of concept of the objective score is like composed by the loss plus the regularization. This like idea or mindset is just like so commonly applied to all different kinds of models. And this is basically the way to help us understanding the whole thoughts like behind the scene. And I think this like very short equation, simple equation really encapsulates a lot of like concepts and the thoughts of like how machine learning works. So yeah, before we go to the last section, which is a pretty short section, do we have any questions?
Loyan, do you know, like in some of those interviews, like how deep the interviewer is gonna question about the theoretical understanding of these boosting methods?
I mean, I think interviews, it kind of depends on where, like say, for example, if you go to a data science interview at Deloitte, the details will be as deep as it can be. So the goal is like for the interviewer to test where is your limit on understanding this algorithm. But like if it's like a startup, which the focus is on like say model deployment, all they expect is like you know how to do XGBoost, like say import scikit-learn XGBoost from scikit-learn, and then fit, transform, and then predict. And then they expect you to write clean code on the data pipeline stuff. Then they may not like ask a lot on the details of the model. But I think it's still good to kind of like understand how this works. And it's a way to kind of like separate you from the other candidates, right? So, and I think that's very important. Yeah, data science interviews are just like so all over the place these days, I feel.
Yeah, thanks. Yeah, I do have found some really tricky interview questions that can be very difficult to answer.
Yeah, and there's so many parts as well, right? Like I had like collected some questions from data science interviews. So it basically ranges from math stats, A/B testing, Python, pandas, NumPy, Python algorithms, machine learning models, deep learning. Like say if it's like a position requires like NLP, then there are lots of stuff on NLP side as well. So it really depends on which position and which team. So it's very hard to prepare for those interviews, I feel, these days. Yeah, anyways, yeah, any other questions? Okay, I think we can just finish the rest of the part and then call it for the day. We don't have too many stuff left. So the rest part, do you want to share your interview question? I mean, I don't have questions. I can show you what I had, but these are not interview questions. These are just like maybe like how to prepare for data science interviews. Let me see if I can find them. Yeah, so basically this is like the structure of the interview. I mean, I'm sure some of you guys are probably doing some like screenshotting and but yeah, I can't zoom in for some reason. I think something is wrong with my laptop, but yeah. So their behavior, product case analysis, project experience, statistics, Python, stats and Python, data wrangling, modeling, specific areas, and take home assignment, right? So there are just so many parts, and I feel like it's impossible to prepare for all these like kind of components. So yeah, I mean, if you find this, you want a copy of this, shoot me a message afterwards. I can share it with you. All right, so the last section is just some other stuff. We don't have anything else at the bottom. It's just like some templates. So other things is for what we went through is a core algorithm. It's called gradient boosting. And then the authors actually spend lots of like effort on making things to run fast and super fast. And I think that's also the secret sauce of like winning so many like Kaggle competitions, because like when things can run parallel and can run fast, you can basically tune parameters, like tune more parameters in a shorter period of time. And also you can do ensembling with the other models. So, yeah, XGBoost, I think there was a period of like, out of like 10 winning solutions on Kaggle competitions, like I think like 5, 6 of them using XGBoost. So these are the things that the author also proposed, but these are more on the hardware acceleration part, which I don't think it will be very interesting to talk about here. And frankly, I don't understanding them like in a very good like depth. So if you are curious, please refer to the original paper. And some resources that I found useful when dealing with like applying XGBoost. So paper documentation, don't need to talk about those. This blog post I found is pretty good. It's about like tuning XGBoost model in practice. So you won't see any of the things related with what we went through today. It's just gonna be a bunch of like, it has a data set, it has some code, has some Jupyter notebooks that you can download and say, okay, first step, you can freeze these parameters and tune these. Second step, tune another set of parameters. Third step, tune another set of parameters. In the end, we want to tune them together. So that's the kind of like the gist of this this blog post. But I think it's very practical. And now I hope you kind of like have a better understanding on those parameters. And if you want to apply XGBoost on some specific method, I think this is a good resource to refer. The reason why I don't want to do a Jupyter notebook on XGBoost is because, you know, like if we just do this kind of stuff, like calling parameters, you can find them like everywhere. So I kind of hope that like maybe that this math looks very like hard to understand at the beginning, but hopefully now you have a better understanding of like how things work like behind the scene, under the hood. So yeah, so that's everything that I prepared for today. Thanks for your time. And if you have any questions, feel free to send. To class extremely unbalanced data, which method will you choose between XGBoost and a neural network? Okay, unbalanced data. I think it's also a pretty big topic of unbalanced data. And if we have time, I think usually I prefer to try both and see which one works better. And also I think the key to address unbalanced data is probably not about like say which model that you use. It's about like say if you need to do some like sampling techniques or either undersampling or oversampling or data augmentation in some way. So if you're dealing with some of the unbalanced data questions, I recommend a package called, I think it's called UBlearn. Is it called UBlearn? No. Yeah, SMOTE is a pretty good way to oversample data, and I think it worked for me pretty well. It is a part of a library called A and B learn, sorry. So imbalance learn. So and they talk like there are lots of like strategies to deal with like an imbalanced data set. So I guess instead of like deciding the models, I would be more focused on deciding what kind of strategy to handle this data set. You're welcome. Yeah, any other questions? Cool. I think that's everything from me. And thanks for having me today. And thanks, Wei Wei and Zoe.
Thank you, and thank you, Lovi and Wei Wei and Zoe. I know it's almost dinner time, so I don't want to drag you guys too long. So yeah, so if anyone have any questions regarding this topic today, feel free to post a question in our Slack channel, and also feel free to reach out Loyuan and all the other presenters. With that, I would like to thank you again for participating in today's lecture, and I will see you guys next week. Thanks.